Welcome. This presentation tells the story of the Emma Maersk incident where a cascade of technical and human failures almost blocked the Suez Canal. Over the next minutes, we'll walk through what happened, why it mattered, and the resilience and lessons that followed, focusing on how small design and process choices can escalate into a global crisis. This slide sets the scene. The Emma Maersk was a pioneering ultra-large container vessel operating a vital Asia-Europe route, and the Suez Canal is one of the world's most critical maritime choke points. The ship photo and canal map help explain why any major failure here risks huge economic disruption, and why this transit demanded flawless coordination between vessel and waterway. At 2141, a routine transit rapidly became an emergency as shown on the timeline map. Alarms and water ingress were reported in the shaft tunnel. Engineers rushed to investigate, and within minutes, the situation escalated from a bilge alarm to a suspected watertight breach, testing the ship's secondary defenses and setting a tense chain of events into motion. What follows is a rapid bulkhead failure illustrated by the photos and diagram. Seawater blasted through cable penetrations, seals failed one after another, and the main engine room flooded. The sudden hydrostatic pressure overwhelmed the intended watertight barrier, creating a torrent that transformed a manageable leak into an uncontrolled flooding crisis. The investigation revealed a weakest link. Incorrectly specified plastic stay plates were used in critical cable penetrations. While suitable for low pressure, these components were not approved for watertight bulkheads, and under pressure they failed well below the required metal plate rating, exposing a gap between approval, installation, and functional safety. The thruster emerged as the catalyst for the disaster chain. Propeller blade fractures and a support plate weakness led to a violent dislocation, creating a large opening for seawater to enter. Post-incident analysis pointed to a latent design and manufacturing defect in the blade root radius, a subtle but critical flaw that triggered the mechanical failure under operational load. This event was not a single error, but a Swiss cheese alignment of multiple failures across layers. Component design, shipyard installation, regulatory oversight, onboard machinery, and shipboard barriers all had holes that lined up. The diagram emphasizes how layered defenses failed together, turning isolated weaknesses into an outcome that nearly cost the vessel. Faced with flooding and loss of propulsion, the master made rapid decisions to steer for the SCCT turning basin, increase engine speed, request tugs, and prepare anchors for emergency release. The map shows that leadership under pressure focused on saving the ship and preventing a catastrophic canal blockage, a high-stakes gamble to buy time and control. The engineering crew fought a losing battle against overwhelming inflow, yet showed ingenuity. They closed watertight doors, activated pumps, and improvised emergency bilge suction when equipment failed, even crawling into flooded spaces to operate valves. The photos highlight both the damage and the crew's quick, adaptive repairs that helped stabilize the situation. In the final minutes, the main engine failed and the crew manually dropped anchors, stopping the ship roughly 15 meters from the bank and averting a grounding that could have blocked the canal. With hard work and persistence, the ship was secured hours later at quay, avoiding pollution, casualties, and a major supply chain disruption. The incident exposed systemic vulnerabilities beyond the broken parts. Flawed design and approval processes allowed inappropriate components to be used. Emergency systems were constrained by single-point failures, and alarm overload impaired human response. These three categories show how technical and organizational weaknesses combine to magnify risk in complex systems. Corrective actions came from multiple stakeholders. Manufacturers discontinued unsuitable components and revised instructions. Thruster makers studied dynamic loads and considered design reinforcements. Classification societies tightened inspection requirements, and Maersk inspected and refitted penetrations fleet-wide while restricting operations until root causes were addressed. In the end, the decisive factor was human resilience. Despite multiple structural and technical failures, the crew's training, adaptability, and decisive actions prevented catastrophe. The near drowning of the Emma Maersk is a stark reminder that designing for perfection isn't enough. Effective recovery depends on well-prepared people who can improvise and lead under extreme pressure.